Ladies and gentlemen, dear colleagues, welcome. My name is Hanzalek, and you are watching the 50th, that's true, 50th talk of the scheduling seminar. So let me ask Mike Pinedo to introduce the speaker.
Okay, our speaker today is Céline Swennenhuis. Céline, so she is from Holland. She got her master's at Delft University of Technology, which is the same university I got my master's. So I know that university reasonably well. She got then her PhD at Eindhoven. Most of you know Eindhoven University. With her advisors were Jasper Nederlof and Frits Spieksma. I always get confused between the Spieksmas. There are two Spieksmas. Both of them start with F Spieksma, but I don't know which. Both of them do scheduling. I wonder if they're family of each other. Then she, after finishing her PhD, she became a postdoc also in Eindhoven with a guy called Bart Jansen. And she is doing work on deterministic scaling with precedence constraints. And she is going to give us a talk today about her work jointly with Jasper and a person that actually I didn't know before, but I suppose I will get to know him, Karel Wojcicki from the Max Planck Institute. Okay, Céline, the floor is yours.
Thank you so much. Yes, thank you for this invitation. It's really a pleasure to present you this this paper. So I first want to explain the problem that we're going to look into today, and then I'm going to explain the results and why I think they're interesting. So let's start with the problem. So I use free field scheduling notation, but I'll also just define it formally. So in this problem, we're given three identical parallel machines, and as inputs, we're given n jobs, and all of these jobs are of length 1, so they're all identical in some sense. However, we're also given a precedence graph, so for example, this one here on the right, where the nodes represent the jobs that need to be processed, and then these arcs represent the precedence constraints. So for example, job C can only start if A and B have finished their job, have finished their work completely. And then the last thing that we need to know is, of course, what are we optimizing? So we're minimizing the makespan. So that means that we're given a number T. And the question is there a schedule of makespan T? Or in other words, is there a schedule such that the last job finishes at T? And for the example that I've created here, there is a schedule. For example, here we have 3 machines and then 4 time slots. And so here you can see in the first time slot, we can only process A and B because the rest is still waiting for something. And then in the second time slot, we can choose between C, D, E, and F. So I chose to do the first 3. And then in the third time slots, well, then F, G, and H are the only ones that are available. So let's do these. And then the last is I and J. So we have a makespan of 4, and this is also an optimal schedule. I don't really care about actually whether it's a decision problem we're talking about or a minimization problem. I'll kind of use that throughout. Like I'll mix it up a bit during this presentation. There's 2 things that I want you to note already, what I've done. And the first thing is that because these jobs are of length 1, I can talk about time slots. So I can assume that every job starts at a complete, like at 0 or 1 or 2 or 3, etc. So I can just talk about the first time slot, the second time slot, etc. And the second thing is that these machines are interchangeable because the machines are identical. So the nice thing is I don't really need to know which job is processed at what machine. I just need to ensure that there's not too many jobs processed at the same time. And the next thing that I want you to note is that actually just this whole graph defines the problem. So it's kind of the simplest way to get a scheduling problem with precedence constraints. You just give this graph, you give kind of like the width that it needs to fit into, and that's kind of a different way to look at this problem. And that's why I think it's a really nice problem. It's really elegant in its way, and it's really small in its input as well. Okay, so there's a different reason why you might also be interested in this problem, and that's because it is on the list of open problems by Garey and Johnson from 1979. So of these problems, it was unknown at the time whether they were NP complete. And for roughly half of them, it's known by now that they are polynomial time solvable, and half of them it's known that they're actually NP hard. And there's two problems left on this list for which it's unknown, and one of them is very famous, the graph isomorphism. And actually, there's now a quasi-polynomial time algorithm for that. And the other one is the problem that I've been talking about, namely the free processor precedent constraint scheduling problem. And in this talk, I'm going to show you that you can also do this in sub-exponential time. So in 2 to the square root n log n order, square root n log n time. So why would we focus on sub-exponential? Let's briefly motivate that. So what is interesting is that typically sub-exponential time algorithms, or at least the square root n type of algorithms, come up in problems, NP-complete problems that have some kind of geometrical properties, such as planar graphs or Euclidean settings, or where they use some kind of parameter that is bigger than the number of vertices. For example, edge deletion to some type of graph. And it's less it's therefore quite interesting that we have a sub-exponential time algorithm, because it doesn't really fall into this category, or at least not in the way that we see it now. And other times where there were sub-exponential time algorithms, it has served as a stepping stone towards a quasi-polynomial time algorithm. So that is kind of what we're hoping for, is that hopefully somebody understands these insights that we had and can get them even further into a quasi-polynomial time algorithm. And that would actually of course, give an algorithm that we might be able to use in practice. So that's the motivation for our problem from the sub-exponential point of view. So what is known about this problem? So what's interesting is that it really depends on whether the number of machines is given as input or not. So if the number of machines is given with the input, then it's actually NP complete. And this was already known for a long time. And it's polynomial time solvable if you have 2 machines. Also, one machine is very obvious. You can just do them in any order, or well, any order that respects the precedence graph. And for 2 machines, it was shown in 1969 already that you can also do this in polynomial time, even when there's like release dates and deadlines involved. And then there's 3 machines, or any other constant number of machines bigger than 2. And so even if you could show that it is NP hard for, let's say, 10,000 machines, that would really be a really interesting result, I would say. But thus far, there's not a lot going on, well, at least not in the exact world. And so before, the best algorithm was actually 2 to the n times n choose m time. And it was just a standard dynamic programming algorithm that would just go over some kind of anti-change, saying like, oh, this is what I've scheduled thus far. Okay, so that's what's known. And then our result is that we can solve it in 1 plus n over m to the power order square root n m time. And for free, that results in 2 to the order square root n log n time that I promised. And it's what might be interesting is that if you're going to look at the paper that is on arXiv, you're going to see a different explanation why we get this 2 to the square root n log n time. And that is because we lately found that there's actually 2 ways to explain this. And the one in the paper is, I would say, a bit more complicated algorithm, but a bit easier analysis. And today I'm going to explain the simpler algorithm, because I think it's just a really nice way to explain the algorithm, but the analysis is going to be a bit harder. So I hope I'll get you all through this today. And the idea, the main insights, they stay the same. Actually, the 2 algorithms in the paper and the presentation today, they're equivalent. So the main insights are, the first is that we're going to use a lookup table. Well, nothing very surprising that is a good idea. The second thing that we're going to use is that there's going to be isolated vertices maybe in our graph, and we're not going to keep track of which vertices we have scheduled, but we're only going to keep track of how many we've scheduled. It's also not a very amazing idea, I would say. It's a kind of a natural thing you would do. And the third one is actually finding a win-win strategy. And also this was done before for other problems. But it's really nice that in this algorithm, you can see all these three combined, and they're all really necessary to get this result. So let's get started. And of course, before I can get started, I need to give you some definitions, because that's how this works. And so let me grab a bit of water. So as I said before, this whole problem is just about a graph, right? So everything that I'm going to talk about is going to talk about a graph. So the first thing to note is that this G is a partial order, and I'm just going to say like it's a drawing, it's a graph, it's a partial order. I don't really care about these things. They're all the same to me in this presentation. And I want to really use these predecessors and successor sets, and they're going to be very natural. Probably you already know what they are, namely the predecessors are everything that's smaller or equal than a certain thing in that set, and everything that is a successor is greater or equal than the things in that set. And then the other things that I'm going to use are the sinks. Those are the ones that do not have any outgoing edges, and the sources that don't have any incoming edges. I'm just going to give an example, because this is where sometimes people get a bit confused. So for example, if I have C and D, then the predecessors C and D are A, C and D, right? Everything that's smaller or equal. And now if I take the sinks of A, C, and D, so then I'm really looking only at the graph with these three jobs. And then within these three, we have C and D as sinks. So that's what I mean when I talk about sinks of a set of jobs. And it's really nice. You already kind of see these two are kind of their duals. Like you can take the predecessors, and then you can take the sinks again, and you end up with the same set if they're an anti-chain, but that's a thing. That's not really necessary. Okay, and then something similar happens for the successors. We can take the successors of C and D, and then we get C, D, and E, and F. And then we can take the sources of these four, and that's C and D again. There's also one other definition I'm going to use, and that is the open successorhood. So kind of like the open neighborhood. I just want to take everything that's a successor, but not in the set itself. And then one more page of definitions. These are a bit easier, I would say. A chain is a set of elements who are comparable. So for example, A, B, and E, they're comparable, they're in the chain. And then I also have the height of a graph, and that is then the length of the longest chain in this graph, and then counted by the number of arcs. So in this example, the longest chain is, well, A, B, and E is one of the longest, but also A, C, E is the longest. But the height of this graph is 2, because in each of these chains, we have 2 arcs. So why is the height interesting? Well, if the height is 0, then there are no arcs at all, right? There's no arcs, because otherwise we would have had at least some kind of small chain. And because there are no arcs, there are actually no precedence constraints. All these jobs are sinks, and we can just schedule them in any order. And that is something that we're going to use as a base case in a couple of slides. Very last, an anti-chain. It's the opposite of a chain. It's a set of jobs that are incomparable. So for example, B, C, and D, they're incomparable, and it's an anti-chain. And we use this in the following way. Sometimes we want to check whether we can schedule a certain set of jobs on a certain time slot, and we want to know that they're not comparable, because they're all then in the same slot, so they can't have any arcs between them. So that's why we want to check that it's an anti-chain. Okay, let's get into the first algorithm. And this algorithm is an algorithm by Doorn and Worn. And it's a pretty old algorithm, 1981 if I'm correct. And it's an algorithm that runs in polynomial time if you have a bounded height graph for a fixed number of machines. And our algorithm will extend that algorithm a bit. So first I'm going to explain this algorithm, and then I'll get into our algorithm. So what is their observation? What do they do? Well, first of all, let me just assume for the rest of this presentation that my schedule is full. I just have a complete full schedule. I don't want to draw like empty slots. If I need to, I can add some isolated vertices to make this happen. But that's just nice for the picture. And what I'm going to do is I'm going to look at where are my sinks in this schedule. I highlighted them blue, for example. And now you can wonder, okay, there's a sink there. Why would I ever schedule a sink? Remember that a sink doesn't have any successors. So it means that it's not really important. Nothing is waiting for it. So that means that I can assume, and this is a bit harder to prove that I'm saying it here, but in general, I can assume that if I schedule a sink here, then everything here on the right is waiting for these two jobs. They're waiting for the other jobs to finish. So either everything on the right is a sink itself, or it's a successor of these two jobs. So let Z be the first moment that we have a sink. Then they say that each job after Z is then a sink or a successor of a job at time Z. So it looks like this. And I have here an approximate because, well, there's one sink here, and you can make that work by changing the formula a bit, but like there's just one job missing here, that's this one sink. So I'm just going to stick with this notation for now. And the nice thing now is that everything on the right is determined. So I can also determine everything on the left, which is just everything except that is on the right. So everything on the left is everything except the successors of H, including H. And there's also no sinks. Important. We're going to use that a couple of times. There's no sinks. Really nice. Okay. Great. So what do Dolev and Wormhoff do? They just guess this set H, and they compute, okay, if I would split the schedule here, how long would it take for the left schedule? How long would it take for the right schedule? Combine it and take the minimum of over all such possibilities. So we have schedule of J. And then if the height of the graph is 0, well, if the height of the graph is 0, so that's our base case, then we can just do them in any order. So we just return the ceiling of the number of jobs divided by 3. And otherwise, oh yeah, I forgot to mention it, it's a recursive algorithm. I guess you guessed that already. So otherwise, we're going to return, and then this formula here. So let me go over that slowly. So we're going to go over all H in sep J. So sep J, that's all the possible separators. So what do they need to abide by? Well, they need to be at most 3 jobs. We need to know that they're all in the same slots. So they need to be an anti-chain. And we need to know that there's at least one sink in them. So we have H without the sink should be at most 2 jobs. Okay, and for each of these H, we're going to compute the left schedule and the right schedule. And then we're going to do a +1 because we also did H itself. And then left is defined here and right is defined here as I did on the previous slide. Okay. So what they use is that in both the left subproblem and the right subproblem, the height decreased by 1. And for the left, I can quickly show you why that's true. And that's because, well, we removed all the sinks. And if you remove all the sinks, then all the chains become one smaller at least. So we know that the height decreases by 1. And similarly, if you go to the right, you kind of remove the left border, as I would say it. So everything was either a successor of H, but H was not in there. So again, you removed at least one vertex from every chain that was larger than 1. Okay, so let's see how the branching tree looks like. So some people, this might be obvious how this looks, but I'm going to do a more complicated branching tree in a bit. So it's nice to have a similar way of showing how a branching tree for this algorithm looks like. So this is a subproblem. And if I'm going to look at all the subproblems that it creates, then part of it is being created because it's a left subproblem, and part of them are being created because they're a right subproblem. But what I do know is that we only had n to the power 3 different guesses for h, right? There were only n to the power 3 different, there are only 3 jobs in this set h, so n to the power 3 possibilities. So in total, there's 2 times n to the power 3 direct descendants of this subproblem. And now, if we maybe continue this branching tree in one part, I'm going to denote the red dots are going to denote my base case, so somewhere where I can compute in polynomial time. Then what I want you to notice that whenever I go down in my tree, I go into a subproblem, so that means that my h decreases by at least 1. So since every time that I go down that is going on, I can only do this h of g number of times, and therefore the number of subproblems in total is 2n to the power 3 to the power the height of the graph, which is n to the order h of g. So pretty nice and simple algorithm. And so we're going to use this as our base. And to do that, I'm first going to slightly rewrite it. It's exactly the same algorithm still. So I still have these sub j, I still have the left and right subproblem. But now what I'm going to do, I'm just going to write it out a little bit more. So I'm going to say for each h in sub j, we're going to compute the left schedule, we're going to compute the right schedule, then we're going to compute what is the minimum over all these possibilities, and then we're going to return it. So what is the first step that we're going to adjust? Well, I already told you it's going to be a lookup table. Not a really hard thing, so that's why I left some spaces here. First, I check if it's already in the lookup table, this subproblem, I just return it. And then if it isn't, we're going to do the same computation. And then at the end, we're going to store it in our lookup table. So we know that we only compute every j at most once. Cool. I hope you all agree this is still a correct algorithm, not really much going on. And indeed, it's not really a lot better. It's still as worse as before. But we're going to do one more thing. And I already told you again what we're going to do. Namely, we're going to store things a little bit differently. So if I look at this graph here, then I see that these 2 vertices are isolated vertices and they're equal. I don't really care if I do L or M. They don't have any successors. They don't have any predecessors. So what I'm just going to do is I'm going to store 2. There's 2 of them. And then everything else I'm going to call the core of J. So anything that has some kind of relation with another vertex or another job, that's going to be in my core of J, and the rest are going to be isolated vertices. And so what am I going to do? Well, I'm just going to store core of J and the number of isolated vertices. And then I'm going to look it up as well if I need to look it up. So store it and then look it up this way if I need to. One other small change that I made, and I hope you're all okay with this, it's a pretty small change. Instead of the base case where I look at the height, I just say if there's no jobs, then I can return 0. Again, I hope you agree with this base case. It's not a really hard base case. This is it. This is the sub-exponential time algorithm. And that is pretty interesting, I would say, because it's not really hard to explain. So why does this help? Why do these small adjustments suddenly make this a sub-exponential time algorithm? So let's see how much I can explain for the coming minutes why this works. The first thing that I need is I want to have a different way of writing our core. So instead of just putting down the whole core, well, I will still do that, but I just want to analyze how many different cores we have in some sense. So what we're going to do is we're going to look at feasible job sets. And those are jobs that sets of jobs that you could actually schedule. Like, for example, I don't want to have A and G in there and then not C in there. Like if A and G are in there, then C should also be in there. That's the only rule that I have for feasible set of jobs. And so, for example, if I have this schedule, then this is also always a feasible set of jobs that belongs to it if I take a subset of the schedule. Okay. And now I'm going to tell you something that probably half you already know. and the other half maybe doesn't. And it's really not something that we came up with, because it's, again, not really hard. But what we're going to do is we're going to say, okay, instead of describing all the jobs, we can say, okay, there's kind of like a left boundary, which are the sources, and there's a right boundary, which are the sinks. And if we take the successors of the sources and then also take the predecessors of the sinks, and we take the intersection of these two things, then we end up with the same set of jobs. So instead of storing all the jobs, I can just store the sinks and the sources of these jobs. So for example, here I would have my sources L and my sinks R. And then again, yeah, I hope you can see that indeed this is the same set of jobs if you take the successors and the predecessors of these two combined. Maybe a more intricate example would be this one. The sources would be L for the blue jobs, and the sinks would be R for the blue jobs. And again, anything that is in the blue is a predecessor of L and predecessor of R and a successor of L, and everything that is not is outside of it. Okay, and now you can kind of see already why it's at least nice that we're not going to incorporate our isolated vertices, because isolated vertices are both sinks and sources. So they take up a lot of space if we want to remember them. And we decided that we didn't really want to remember them. So instead of that, we say J can be described as this. We just say, okay, we want to only look at the core of J. And then still we can do the same thing. So we still have a left boundary and a right boundary. And this is where we say, okay, we have two isolated vertices. Okay, and then there's one more observation that is not directly clear maybe. And that is sometimes instead of taking the sources as my left boundary, I can take something slightly different. And in this case, I can take the set, just the vertex A. So like this, and then say that we have to take all the open successors of A. And then I still describe the same set of jobs. So instead of really taking the left boundary to be the boundary that was included, I can also take kind of the boundary that was just before. And that's how I can say that, for example, this case, core J is now successors of L with open neighborhoods. And then L is in this case just A. Okay, how to use this? Let's see. If we go to the right, if we go into a right subproblem, what happens? We have this decomposition. And now here on the right, we know that everything here is a successor of H1. So we can use that as our left boundary. So J1, the core of J1, is the successors of H1. And we can keep the right boundary because the right boundary didn't change. It's still the same set that's kind of bounding it off on the right side. And the nice thing is that this H1 is only of size 3. Size 3 is something that we can handle. That's only three jobs that we need to remember. And well, I already said, like, okay, I do need to take into account a bit about this vertex here, the sink that is being scheduled. I need to remember that I do not want to, I already did that one. But the nice thing is that this vertex is a isolated vertex with respect to the graph that is here on the right, because it was, well, it's not a successor of H1. So it has to be kind of like an isolated vertex in that part. So I just need to remember, okay, I already did one isolated vertex. That's what I kind of remember. Okay, what happens now if I would go to the right again? Well, the nice thing is exactly the same thing happens. So I can go into this subproblem to the right again, and now everything here, I can keep the right boundary again. And my left boundary now becomes H2. Again, H2 is only of size 3. And now all these vertices, in this case 3, if I would consider them in the right subproblem, they would be isolated vertices. So if I now just remember, oh, I already did 3 of them, then that defines my whole problem on the right. And I can keep doing this, right? I can just go right again, and then I have an H3. And again, H3 is of size at most 3, and there's maybe some vertices that I already did. I just need to remember how many I did. So there's two two key takeaways. The first one is that every right subproblem has a left boundary that is of size at most 3. And the second thing is that there's actually at most n to the power 4 different right descendants. So let me first give you an idea what a right descendant is. A right descendant is a subproblem that if you go right, you're still a right descendant of the original problem. And because if I look back at my H3 here, this whole set was only dependent like on H3 and R. It doesn't use H2, it doesn't use H1. And so there's really only n to the power 4 possibilities, namely the size of H and then one more for the number of isolated vertices. So that's the two key takeaways. And similarly, we can do something if we go to the left. Namely, if we go to the left, we can keep our left boundary. And there's a new right boundary. I can't really say a lot about our right boundary yet, but that's, or not really, yeah, that's something you'll see later. But the left boundary, I can just copy from before. So if we have that every time we go right, we have a left boundary of size at most 3. Well, that kind of carries over to our left problems because we kind of keep the same set there as well. So every left problem also has a left boundary of size at most 3. And the nice thing, and here again, I use the same trick, I removed all the sinks. There's no sinks in here. And the sinks, everything in the right boundary was a sink. So I removed all the sinks, so I removed all of R. And this is kind of where our win-win strategy comes in. Either there's going to be only a few sinks, but then my problem is pretty small to describe, or there's going to be a huge of them, but then if I go left, I lose a lot of these sinks. And that is the win-win. So I'll just go through that a couple of times because it doesn't, yeah, it's not maybe directly clear why that is true. So the invariant is that we can describe any, we can describe the core of any set J that we're seeing as the successors L, and then L is at most 3, the size of L is at most 3, and then some R, and then K isolated vertices. Well, this is at most of size 3, and these, yeah, you can describe it with just a number. And then this R is where we're going to develop this win-win strategy. So if R is smaller than square root n, we're totally fine. There's not a lot of subproblems that are of this type because, well, there's only n choose square root n different R's. So there's 2 to the order square root n log n different R's that are subproblems that are of this type. And if we go left, then it's nice. If we have something that is R is bigger than square root n, then we know that if we go left, we make a lot of progress. How does this look in a branching tree? And this is why I'm happy that I already showed you a branching tree, because this is going to be quite a complicated branching tree. So I'm going to make the red nodes, that's everything where R is at most square root n, and the black nodes are those that are bigger than square root n. And let's just follow some subproblem. And then maybe at one point it ends in, or it maybe not ends, but it finds some kind of subproblem that follows in the red category. So there's not a lot of sinks. Okay, well, either this was already in the lookup table. If it was already in the lookup table, then we can think of this as a base case, which is nice, because then we can solve them polynomial time. Just look it up. Or it's not yet in the lookup table, but that can only happen once. And to analyze this in a way that makes sense for us, we're going to view it as its own tree. So whenever we have a red vertex where still a tree is attached, we're going to kind of cut it up into 2 trees. And then each of these trees we're going to analyze separately. And since there's only a small number of different red problems, there's only a small number of such trees. Okay, I hope you're still fine with this, because we're going to continue with just analyzing one of such trees. So a tree that starts at a red vertex, and whenever we find another red vertex, we can kind of use this as our base case, because either we just consider it as a different tree, or it is actually already in our lookup table. So let's start with some vertex. At first, I'm going to look at what happens if I go right, and maybe right, and then maybe from that one I go right, and then right again. But I already told you can't do this a lot of times, because there were only n to the power 4 right descendants. There was only a polynomial number of ways to go right without going left. And now I'm going to draw everything where you first go left. So I call this the first left descendants. So those are the subproblems achieved by going right and then once going left. So it's the first time that you go left viewed from this original vertex here. So I claim that there's only n to the power 7 of them. And that is because we have only n to the power 4 right descendants. And each of these only creates n to the power 3 subproblems, because times 2, I have to say, but let's, yeah. So there's a n to the power 3 different ages that you can get. And then if you go left, so that, yeah, the total is n to the power 4 of these problems that create each n to the power 3 subproblems. So you get n to the power 7 subproblems where you first went left, viewed from the very first vertex. Okay, and now note that in almost every one of these red arcs, every time I went left, I made square root n jobs progress, because except for this one vertex where I only have at most square root n vertices in R, all my other vertices in this graph should be a black vertex. And whenever I go from a black vertex down, it means that I made square root n progress. That was my left, inside of my left subproblems. And so I think you can already feel where this is going, because you can't keep doing this, right? Every time that you go left, you make square root n progress. So I'm just going to draw a level down whenever I go left, and I can only go left at most square root n times. So my whole graph, if I draw it like every time you go down, if you go left, it has square root n levels. And I have a degree kind of from going one level to another of n to the power 7. So that means that the number of subproblems in this tree is n to the power 7 to the power square root n. There's actually a +1 here that I've got, but yeah, I think you can forgive me for that. But this is, of course, only this tree. And there are many trees that start at a red vertex, but because we only have a 2 to the, n to the square root n of these trees, it's all the same. We still get the 2 to the order square root n log n different subproblems. So yeah, that's pretty cool, I would say, because it's still the same algorithm. I'm just going to present the algorithm again because I'm really a fan of how you can just like show it in this such a simple way. You just store the core and the isolated number of isolated vertices. If it was already set, then you just take it from your lookup table, and otherwise you just find 3 jobs. You just split it into 2 subproblems, compute each of these recursively, and then once you've computed it, you just store it in this way in the subproblem, in the lookup table, and that's it. That's it. Yeah, and so even though there might be, in theory, there might be lots of problems that you could create, we're only creating 2 to the order square root n log n of them. So there's some corollaries. Officially, our result looks like this. So PM, so for any constant m, then this is the runtime. Well, constant m is, yeah, depends on how you see it, but for any m, this is the runtime. And the first thing is that whenever the number of machines is sublinear, then this is actually sub-exponential time. So that's pretty cool. So we're really improving for many m's the best runtime for this problem. And the second corollary is that when the number of machines is given as input, We can again develop some win-win strategy with a fast subset convolution algorithm, and then we can get a 1.997 to the n poly n time algorithm. This might not be clear for everyone why this is interesting, but it has to do with that not a lot of problems allow for something that is faster than 2 to the n. So this is one of the problems that we can show that it can actually be solved faster than 2 to the n. To conclude, our main results: 3 machines can be solved in sub-exponential time. And the key ideas again were these 3 all pretty simple things, but really nice when you combine them. We have a lookup table. You don't store isolated vertices, you just store the number of them. And then you find this really nice win-win strategy using the number of sinks. Yeah, that's really all the ideas, and it's really nice. There's open problems. Of course, there's always open problems. The first one that I'd like to mention is a quasi-polynomial time algorithm. We've been searching for this a lot in the last year. We haven't found it. So we really hope that this would give us the stepping stone that I was talking about earlier to get this quasi-polynomial time algorithm, but it didn't thus far. So if you're interested in this, please read our paper and make that happen, because I think it would be I would like to throw a party if that happens. I believe that it's possible. And the second thing is that there's a lot of research as well on approximation algorithms on this problem. So a big open question is whether a p-test exists for a fixed number of machines. And lately there has been quite some progress by, now there's a q-p-test. It was first found by Garey in 2018, then Céline in 2021 improved it. And then there's like a simpler way to look at it. But the best now is a 1+ epsilon approximation in this time. And yeah, again, that's also that they use a lot of insights as well, where they kind of have either there's large height or there's small height, and you can kind of balance between these things. So I really hope as well that maybe some of our insights can help them to get faster algorithms. And I think that's all that I'd like to tell you. So thank you so much for listening.
Okay, thank you very much. And now we'd like to open questions, so you can unmute easily, I think, if you have a question. Oh, Lars is uploading, but Lars, you should ask questions that would help us more.
I have a question, actually. Thank you very much for the nice presentation. It was really a pleasure. So you have this really simple algorithm in some sense. It's just caching some sub-problems, and you have an analysis to estimate how many sub-problems are somehow considered. But do you have any idea if this analysis is tight? Like, could it be that the same algorithm also gives you n to the, I don't know, something better, you know?
That is a very good question. Thanks, Lars. I think we've tried to analyze this, and I think we're in a worst case when it's kind of like a grid, like you kind of go bigger and then smaller again, kind of like a grid, but then like turn 45 degrees. I think then I think I remember that then you actually get the number of sub-problems that we're considering. Maybe not the full grid, but maybe a subgrid of it, and then things like that happen. We did have some theory on how to avoid it for that particular case by having a slightly different algorithm. But yeah, we're still not completely understanding that ourselves. Like what is now the hardest case for us to solve? That is something that we're still searching for.
Thanks a lot.
Okay, thank you. Any other question?
Okay, let me ask you a question. Céline, what is the status of, in your ideas, the total completion time, summation Cj? So again, with precedence constraints, Pj is 1, 3 machines.
Right.
I presume you probably already have looked at it. It probably is an order of magnitude more difficult, but will you get again a sub-exponential time?
Thank you so much for the question. Yeah, we've also looked at this. Now I need to remember correctly. So I think it would still work because the idea of this decomposition where you can split it, when you interchange things, you really interchange, like in the analysis of why you can assume that you kind of interchange things. So if there's a sink and there's still something here that is not a successor, then you can kind of interchange their places. So that would not increase the sum of completion time. So I think, but it's not stated anywhere like very rigorously. I think the same decomposition would also work for sum of completion times. And then if the decomposition works, I don't think any of what I presented would not work for sum of completion times. So
so it is your next paper, okay. Yeah.
Who knows? Yes.
There's always next paper, don't worry. Okay, any other question?
Yeah, can I ask a question?
Sure, yeah, go ahead.
Perhaps it's a stupid question, but people say that because of what is known about graph isomorphism, it is unlikely to be NP-complete and unlikely to be polynomially solvable, but it will probably be in between. Now, I don't say that I understand this, but it is being said, and I heard it. And what is the status of this P3 problem? Is that what do you believe? What is your conjecture there? Do your results make it less likely that someone will prove it NP-complete, or will it turn out to be in between? What do you think?
Thank you so much for your question. I am wondering exactly the same. So I have to say as well, I don't exactly get what is the consequence of this quasi-polynomial time algorithm for graph isomorphism. But the only thing that I do know is that I've looked at this problem for a really, really long time, and I don't think it's a hard problem. I don't think it's a polynomial time problem. That's my feeling with how long I've stared at it and the different cases that I've considered that are just not easy to solve. But on the other hand, yeah, I've also didn't manage to get any hardness results in the last 6 years. So it might as well be in between. Yeah, I once was very sure that it should be polynomial, and then I think a week later I was getting sure that it should be NP-complete. I don't know by now. I really don't know.
Just open. It's just open. Okay,
very open.
Yeah. Okay. Good. Good to know. I'm still hopeful.
Me too. Yeah. If there is ever someone having a polynomial time algorithm, I actually promise to celebrate this. So keep me posted.
Thank you.
Okay, thank you. Any other question? If this is not the case, thank you, Céline, once more for your talk, and thank to all the other listeners that they participated in this seminar. I have no announcements because we have not made a schedule of winter talks yet. So we have to work on it with Michael. If you have some suggestions, don't hesitate and send us some suggestions of good speakers. And we will meet probably in the second half of January. So I wish you Merry Christmas and Happy New Year. And stay tuned. We will announce the talks soon enough. Okay. Thank you.
Well, emphasize the fact that we would like to hear suggestions for speakers the end of January, beginning of February.
Yeah, because
so if Uwe Schwegelsohn or Sergei Sebastianov, if anybody in Novosibirsk or in Dortmund would like to speak, I say let us tell us who the names are and what the topics are.
But it has to be extremely attractive and important for scheduling community. That's the rule, right?
You saw today the quality of the PowerPoint of Céline. She made me a little bit jealous with the quality of her PowerPoint. We have to, but okay, that's the quality of the PowerPoint we expect.
Thank you.
Okay, thank you very much. Let me conclude the session and have a nice evening or day. Thank you.
Okay,
Bye-bye.
thank you.
See you.
Thank you so much.
See you.
Thank
See
you.
you.
See you.
Yeah.